Are you talking to me, Ruwei? I see you moving your lips, but you're muted.
Yeah, so I suggest that we wait for maybe 1 more minute.
Sounds good.
Then we can get started.
Okay, should I share my screen in the meantime or not?
So I will first share screen and then I will ask you. Yeah,
Sounds
thank
good.
you. Okay, let's get started. And welcome everybody to the MIDAS IOE co-presenting seminar series. So today we are very glad to welcome Professor Phebe Vayanos from the University of Southern California. Phebe got her PhD in operations research from Imperial College London. And she's currently an WISE Gabilan Assistant Professor of Industrial and Systems Engineering and CS at USC. And her work is motivated by AI in social problems in general. And Professor Vayanos, it's very great to have you here present to us today. And I would also like to mention some upcoming MIDAS events shown on this slide. And without further ado, let me stop sharing and ask Phebe to present her slides and start her seminar.
Thank you so much for the kind introduction, Ruwei. I really appreciate it for organizing also the very nice meetings today. Let me start by asking, I realize we started a little late. Should I stop a little bit earlier? So should I plan to stop at the planned time? So kind of present up until 50 past the hour and then leave some time for questions, or like, so what's your advice?
I suggest you could use the like the whole 50 minutes if you need, because this event is recorded.
Okay, sure. Then I'll go ahead and present in the with the length originally planned is what you're saying, right? Okay, sounds good.
Thank you.
I'll do that, and if people need to step out, don't hesitate to do so. I will not be offended. I understand that we started late. In any case, thank you everyone for joining today. I'm really excited and honored to be here. So as Ruwei mentioned, I'm with the University of Southern California, where I'm an associate director of CAIS, the USC Center for AI in Society. And today I'd like to tell you a little bit about my work on designing robust, interpretable, and fair social interventions. So a little bit first about my group. My group is part of CAIS. This is an interdisciplinary research center between the schools of engineering and social work at USC. We conduct research in operations research and AI with aim to help tackle important problems that our colleagues in social work are faced with. Our mission is to collaborate with communities for a more just, healthy, and sustainable world. I see I have a chat question. Oh, this is probably not for me. So in my research group, we take an end-to-end research approach. What this means is that we involve our community partners and policymakers throughout the research process, from the problem definition, where they explain to us the biggest problems that keep them up at night, to understanding the data, all the way through the mathematical formulation, the solution approach, and finally the intervention. Our ultimate goal being to make an impact in the real world to solve the problem that our community partners and policymaker collaborators are faced with. In the process, we actually develop methods that can also be applied to problems different than the one that actually motivated our work. When we're designing algorithms that are impacting people and that we're aiming to deploy in society, there's three main things we need to be concerned with. So one of them is this idea that we'd like our algorithms to be optimal and robust, meaning that they'll perform as well as possible, even in the presence of unmodeled phenomena or of uncertainty. We'd like them also to be fair, in some sense that's appropriate for the application, and interpretable. And again, here to help design algorithms that satisfy this desiderata, we work closely with our partners to help define what interpretability means in their context, what fairness means, etc. Today, I'd like to tell you about two projects that I've been involved in. The first one is concerned with designing policies for allocating housing to people experiencing homelessness, and in collaboration with the Los Angeles Homeless Services Authority. And the other one is concerned with biodiversity conservation, and this is in collaboration with Panthera, an organization dedicated to protecting wildcats. The motivation for this first project is the homelessness crisis that many of our US cities are faced with. This includes LA, which has about 60,000 persons experiencing homelessness, and at the same time has a severe shortage of resources with only about 21,000 housing units being offered any given year. Not only we have scarcity of resources, but there's also severe inequities in housing. In LA, for example, we have Black people being disproportionately affected by homelessness. They represent 40% of the homeless population and only 9% of the general population. For this work, we're partnering with the Los Angeles Homeless Services Authority, which is the entity in charge of allocating housing resources in all of LA County. So this is us meeting with policymakers at LAHSA in LA. For this work, I'm working very closely with this person here, Eric Rice, who's co-director of CAIS and a professor in the USC School of Social Work, who's an expert in homelessness. So I mentioned we need to be very thoughtful, given the resource shortages, about how we allocate these very scarce resources, right? There's a big ethical dilemma of who we should be prioritizing. So how are resources currently allocated? Well, the recommendation is the following. When someone enters the system, they should answer a survey. So here I'm just showing the first few questions of this survey, which asks quite personal questions about people's previous experiences, with aim to try and assess their vulnerability. Depending on how you answer each question, you get a score. The scores get added up together to give a single vulnerability score. Then, based on this vulnerability score, you get partitioned into three buckets, with people who are the most vulnerable being prioritized for the most supportive kind of housing resource, called permanent supportive housing, or PSH. Those who score in the middle being prioritized for the second type of slightly less supportive resource called rapid rehousing, or RRH, and those who score the lowest are receiving services only. The main issue with this score, although being quite interpretable, this policy is actually not tied to outcomes, and it's not tied to arrival rates of individuals nor resources. What does this mean? Well, actually, if you were to simulate implementation of this policy, you would find that many people who are most vulnerable never get PSH. They actually get nothing, just because there's not enough resources to come around. At the same time, this policy, although it prioritizes those who are most vulnerable, it does not necessarily make best use of available resources. Indeed, it could be that some people who are the most vulnerable actually could exit a homelessness by being assigned a rapid rehousing resource. Conversely, some people in this bucket may need permanent supportive housing to exit homelessness. So there is a need for a better mechanism for matching people to housing resources. In our first discussions with the Los Angeles Homeless Services Authority, we tried to understand what they would like the policy that they have to be doing. And they really mentioned 3 desiderata. The first one is, of course, efficiency, that they'd like to make best possible use of their resources to have, for example, as many people as possible exit homelessness. That said, what we have access to is just observational data that shows what happens to individuals who enter the system. As it turns out, people follow very complicated trajectories in and out of homelessness, making it difficult to judge if someone had a good outcome or a bad outcome. Similarly, they mentioned that they like the policy to be fair. That said, it's not very clear what fairness means. Indeed, we could have fairness in terms of access, so in terms of allocation of resources, or fairness in terms of outcomes. And even what this means is not entirely clear. As a motivation, in the current system, it was found that all the resources are given at equal rates to Black and white individuals. Actually, Black people return to homelessness at twice the rate of their white counterparts. Finally, they'd like the updated policy to be interpretable. Indeed, you can see that the current policy is quite interpretable. It's very natural to prioritize people based on vulnerability. So we'd like to preserve this idea that we'd like to be able for someone non-technical to see the policy and understand why someone received a resource in priority over somebody else. The main challenge, of course, when you want so many things from a system that you design is how you can prioritize these conflicting objectives, right? Indeed, when we have very few resources, it's very hard to understand what the trade-offs in view of these different objectives should be. And in fact, it seems that this is a recurring challenge in terms of the that they have to discuss repeatedly at LAHSA during their policy committee meetings. What we propose to do is to use a technique from marketing to try and understand the preferences of policymakers in view of these conflicting objectives. This is the idea of preference elicitation. The idea here is to ask policymakers to tell us which policy they would prefer between two. So for example, here we're showing policy A on the left and policy B on the right. And we would ask from the policymaker, do you prefer policy A or policy B? This is a very toy example where we're just comparing fairness of the policy in terms of the outcomes and efficiency of the policy. For example, the policy on the left is quite unfair in terms of its outcomes by race, but it's quite efficient in that for an arbitrary individual in the system, they would have over 70% chance of exiting homelessness. Policy B, on the other hand, is quite fair, but not so efficient. So no matter what your race is, you have a pretty much 50% chance of exiting homelessness, but overall efficiency of the system is quite lower than before. Actually, this idea for eliciting preferences has also been used, perhaps you have heard, in the context of the MIT moral machine, which was trying to understand how self-driving cars should make decisions when faced with ethical challenges. For example, they had to decide whether to save a baby or an older person. So whether they should swerve and save a baby but kill the older person and vice versa. So here we're using this idea in the context of policy design. The main challenge, though, when trying to elicit preferences is that we have a very large number of possible pairwise comparison questions we should ask about, right? And at the same time, you know, if each query takes about 30 seconds, let's say, to answer, we can't, you know, spend hours and hours with our policymakers asking them such pairwise comparison queries. First of all, they would get tired. And second of all, they would start giving us responses that are more and more inconsistent because of tiredness. They also don't have infinite amount of time at their disposal. So the key question we're trying to answer here is which questions, which pairwise comparison queries we should ask to gain the most useful information. Although this problem has been studied in the literature, both in the AI literature, in the operations research literature, and in the marketing literature, the approaches designed have not been tailored to a specific recommendation problem. Here, there is a specific problem we wish to solve, which is the problem of recommending a single policy. So we'd like to design queries that are going to be as informative as possible for that specific decision-making problem, and that are going to be robust to uncertainty, meaning that even if we're not able to fully learn the preferences of our policymakers, we're going to be able to make a recommendation that's as good as possible. So let me now start discussing the various building blocks of our model. First of all, we have the candidate policies. So these are policies that we'll be able to use to build queries. Each policy is going to be characterized by its features. We assume that we have J features, and each feature is going to be a measure of interpretability, efficiency, or fairness. So for example, this vector of the features of the policies could include, let's say, the chance that you exit homelessness if you are white, if you're Black, if you're Asian, the chance that you exit homelessness overall, the minimum by race, the minimum by age, and so on. We can use this set of candidate policies to build queries. What's a query is nothing more than a choice of two policies from this set. So for example, we could ask our policymaker to compare policy 3 and policy I, and to tell us if he prefers the first one, the second one, or if he is indifferent between the two. So basically, we are going to have to choose comparison queries, which are nothing more than pairs of items. Our ultimate goal is to make a single recommendation to our policymaker, and the recommendation will come for the recommendation set. So intuitively, this is the optimization problem that our policymaker wants to solve. They're trying to determine the policy that's going to be the best for their utility, that's going to maximize their utility. So in the recommendation set could actually be a discrete set, so where we need to recommend one policy from a finite set, or it could be a polyhedral set or the intersection of the polyhedral set with some integrality constraints. And what we'd like to do is to recommend a single policy from this recommendation set. Throughout this talk, I'm going to assume that the user is rational. I'm going to relax this in the paper, but I won't have time to discuss this today. So this is just to minimize notation and for ease of exposition. I'm going to assume that we can represent the preferences of our policymakers using an unknown utility function U, which is nothing more than a mapping from the set of covariates to the real numbers. And because our user is rational in this simplified setting, if they say they prefer policy X over policy Y, this really means that their utility for X is greater than their utility for Y. If they say they are indifferent, it means that the two utilities are equal. Following a long line of work in artificial intelligence, operations research, and in marketing, we're going to assume that uncertainty in user preferences is not modeled using distributions, but rather uncertainty sets. This is very much aligned with how robust optimization models uncertainty. The motivation for this is that we don't have any data when we begin with about the preferences of our policymakers. All we can do is, for example, say that, oh, we don't know anything about their preferences, or maybe encode a few things that are very well known, such as, for example, that we prefer, let's say, having higher efficiency rather than lower efficiency. We're also going to assume that our utility function is linear. This may seem like a stringent assumption at first. However, it's actually compatible with many choice models from the literature. In addition, because we don't require independence in the covariates, we can here take nonlinear functions of the covariates, and our approach will carry through. This means that our utility function will ultimately be nonlinear in the covariate. All that we require is really that we are linear in the utility function coefficients. This vector of utility function coefficients is what's going to be unknown. And we're going to assume that it lies in an uncertainty set that I'm going to call U0. This set is just going to encode any information I have at the beginning before asking any queries from the policymakers. And I'm going to assume that this uncertainty set is polyhedral. Our approach could generalize to more sophisticated sets. Some examples: if I don't have any information, I can assume that U lies in the -1, 1 box in J dimensions. The reason is that we're going to have the same solution even if we scale this uncertainty set. Alternatively, we could assume that we have normalized the utilities so that no matter what features we have, the utility of our user for any of the items will lie between 0 and 1. So now let's try to understand what happens as we ask queries from our users. So to illustrate this idea, I'm going to assume that we have a two-dimensional feature vector. So each item is characterized by 2 features, and that we have 3 items, so 3 policies that I've depicted here on the top right. Let's say that I ask you, do you prefer policy 1 or policy 2? Really what I'm asking is where you're on which side of the hyperplane with normal vector x1 minus x2 does your utility vector lie? So effectively, I'm saying, does your utility vector lie on this side of the hyperplane or on that side? Let's say you prefer item 1, then I know that your utility vector is on this side. I can do the same, asking more questions. So for example, here I asked you prefer policy 1 or policy 3. Let's say you prefer policy 3. Now I know that this is the updated uncertainty set. So basically I know for sure that your utility vector lies in this set. Something nice to observe is that this uncertainty set, it depends both on the queries iota I asked and on the responses S to the queries that you gave me. So although I cannot control your response, I can control the choice of queries. As I start asking more queries, I'm refining basically my knowledge of your utility function, U. In particular, I know that analytically, I can write my updated uncertainty set as follows. It's the initial uncertainty set augmented with 1 constraint for each query I ask you. And the only thing that changes as I ask more queries is the sign of the constraint I add, which depends on the answer you give me. So when we're making recommendations under uncertainty, there's 2 ways in the literature that we can do it. And why am I saying that I'm making recommendation under uncertainty? Because even if I were to ask you all queries, it's very likely that I still won't be able to exactly know what your utility function is. And so it makes then sense to make a recommendation that's going to have the highest possible utility in view of uncertainty in your utility function or utility vector U. So one possible way to handle this is by maximizing worst case utility and solving the following optimization problem, or minimizing worst case regret, where basically we want to minimize the worst case of the regret, which is nothing more than the difference between the utility of the item I should have recommended to you and the utility of the item I actually recommended. In this talk, I'll focus on max-min utility, but the ideas extend pretty easily to the min-max regret case. I'd like to pause at this point and ask if there's any questions from the audience. All right. So now that I've laid out the various tools of my model, I'd like to go ahead and tell you how I'm going to choose queries. So we're going to investigate two ways of selecting queries. One is an offline elicitation approach that basically is going to select all queries in advance. And the other one is an online elicitation where we're going to be able to adapt the choice of queries to the answers we see. So in the offline elicitation setting, we decide all queries to begin with. We then observe the answers to the queries, and then we recommend a policy. This is suitable for paper-based surveys that are very common in low-resource settings, or if all people must be asked the same questions. In general, this is a problem that can be solved offline. This is applicable when the problem must be solved offline. I have a question from the audience. It's asking, is there any limit on the number of questions? Yes, great query, great question, Vayanos. So indeed, we assume that to begin with, there is a finite number of queries that we can ask. So in the offline elicitation setting, I'm going to say I have k queries I can ask, and I'm going to choose which k queries that should be. Let me know if that didn't answer your question, Vayanos. So now we're ready to formulate this problem mathematically. So mathematically, this is a sequential decision-making problem, right? I first ask some queries, then I observe the answer to the queries, and then I solve my recommendation problem, where my recommendation problem uses the information I got in the query stage. So effectively, we select query in a way that's going to maximize our worst case utility, where the worst case is taken over the answers that we'll receive, provided we make a recommendation that is optimal. So a bit of technical details here. This set S of I just says that the responses that I receive must be compatible with some utility vector. In other words, the person who's answering me must be rational. And again, if we had inconsistencies here, all that would change is the way in which we define this uncertainty set, but otherwise everything is the same. So what's unique in this problem relative to how it has been tackled in the literature is that it couples directly the choice of queries with a downstream recommendation to ask queries that are going to be as informative as possible for this downstream problem. In contrast, existing approaches from the literature, they are optimization based as well, but they focus on reducing uncertainty around the utility function, which we argue here is different than asking queries that are going to best inform the recommendation problem. In terms of complexity, we have the following result. We show that if the recommendation set is convex, our problem is going to be polynomially solvable. And actually, it doesn't really help to ask any questions in the worst case. On the other hand, even evaluating the objective function would be NP-hard if the recommendation set only consists of 2 items. This motivates us to focus on the case where the recommendation set is discrete and to obtain a mixed binary linear programming reformulation of our problem. Although in principle, standard techniques from robust optimization could be used, there are a few challenges. The first one is that both this uncertainty set and this uncertainty set are decision dependent, and even this one depends on the uncertainty from the previous stage. In addition, this uncertainty set is open. It involves strict inequalities, which for the optimizers out there is a bit of a challenge. In addition, we show, however, that we can make a few simplifications. Actually, let me go back. We can remove the dependence of S on iota here and leave the objective value unchanged and the set of optimal solutions unchanged. We show that we can relax the strict inequalities here and that we can drop the indifferent answers from the response set, which substantially simplifies the problem. And then using traditional techniques from robust optimization, we can rewrite our problem in this fashion. This is an MBLP, a mixed binary LP, that can in principle be solved with Gurobi. However, it's a very large problem as the number of queries grow. So the kind of queries we're interested in, the kind of values of number of queries that we're interested in is 8 to 10. These can be answered in reasonable time. Even for this problem size, though, it becomes quite challenging to solve this problem because both the number of decision verbs and constraints are exponential in K. This motivates us to develop a tailored algorithm based on column and constraint generation idea. So we start by solving a relaxed version of our problem that involves only a subset of the possible response scenarios. We obtain a set of candidate queries iota. We plug these into a feasibility subproblem, which we solve. And as a result, we either obtain a violated scenario or a certificate that this set of queries is actually optimal in the original problem. The reason why this works quite well is that in practice, only a few of the scenarios are going to be relevant in the relaxed problem, in the main problem. For the online elicitation approach, this is a harder problem because this is now a sequential decision-making problem with multiple time periods and endogenous uncertainty. It is practically relevant when looking at computer-based surveys and when we're happy to ask different questions from each individual. We must be able to solve it online. Because this problem is very challenging, we propose a conservative solution approach that we solve a sequence of 2.5-stage problems, just like the one I mentioned earlier. So we're going to select questions one at a time, as if they were the last questions we're going to ask, but again, by melding together the query and recommendation problems. Let me now move to my numerical study, and I'll focus on the real data case. And in particular on the problem we are faced with our collaborators at LAHSA. So our collaborators at LAHSA gave us data from what is called the Homeless Management Information System. So this is a system that collects information on all the individuals that were waitlisted for housing and their answers to the VISP-DAT and then their demographic characteristics. We denote this by XI. It also shows the treatment the person received, so the housing resource they got. We denote this by KI. And finally, it also records the outcome from the match, whether that person successfully exited homelessness or not. The issue is that this data has been collected in deployment. So we are not in a randomized clinical trial setting. In particular, the characteristics of individuals were used to decide on treatment assignment. This historical policy is not in our control and is in fact unknown. So this is a setting where we can only observe the outcome under the treatment received. We don't know what would have happened to an individual if they had been given a different housing resource than the one they actually got in the data. This means we're going to have to use techniques from causal inference to evaluate the performance of any given counterfactual policy, meaning a policy different than the one that was used to assign treatments in the data. What we propose to do is to look at various candidate policies that could be of interest to the policymakers in the sense that they optimize different trade-offs between fairness, efficiency, and interpretability. The way we do this is that we're going to use an optimal prescriptive trees approach that we have recently proposed, where basically a prescriptive tree is nothing more than a classification tree, but where instead of making predictions at the leaves, you assign treatments. And so we're going to design such prescriptive tree policies that are going to optimize some desirable outcomes, again, trading off in different ways, fairness, efficiency, and interpretability. In order to use that method, we need to obtain predictions of various elements. In particular, we need to learn from the data what are called the propensity scores. This is basically trying to predict the probability for each individual that they would get the treatment they actually got in the data. I'd like to argue that this prediction needs to be fair, meaning that we'd like to have equal error rates of any type no matter what your race is, equal error rates of any given type, so true positive rates, false positive rates, etc., no matter what your age is, and no matter what your gender is. So let me show you our results. So on the figure here, so this is again results just on this learning phase. On the figure here, I'm showing on the x-axis equalized odds, which is this metric of fairness that measures differences in error rates between age groups, race groups, and gender groups. The smaller it is, the more fair our model. And on the y-axis, I'm showing accuracy. So the higher the number, the more accurate our model, the better it is. With the triangle and circle that are not colored, I'm showing the performance of classification and regression trees. And what we can see is that whether we're looking in or out of sample, that this approach is quite unfair. It results in essentially the worst possible degree of unfairness, meaning that for some groups, I'm going to have an error rate of 1 and for others 0. In contrast, we can see in color our proposed approach for learning optimal and fair classification trees that I'm showing here at the bottom, where we can see that basically by changing this input bound for fairness, I can completely tailor the trade-off between fairness and accuracy of our algorithm. In particular, we can see that we can get fairness for free, essentially, or quite a bit of fairness for free by just imposing this fairness bound and not losing any accuracy. After a while, if we want something that's very, very fair, we will start paying a price of accuracy, but still we can have quite reasonable models. Here I'm showing the model we ended up using for propensity score, which is up here. This is actually quite interpretable. It's showing that, for example, if you have been unhoused for a long time and you have high comorbidity score, you should get, you do get rather in the data, the most supportive kind of resource with probability 68%. And in general, the more vulnerable you are, we can see that the more supportive the resource you get. In addition to learning propensity scores fairly, we had to learn the outcomes conditional on no treatment, the outcomes conditional on PSH and on RRH. And in all cases, we can see that our algorithm can yield solutions that are a lot more fair than existing methods. I'm going to skip through these slides. The results are very similar to what I showed before. And now I'd like to show you results on our preference elicitation approach. So here, what we did, right, is generate using the prescriptive trees approach and using the fair models I just showed you, candidate policies that have different trade-offs between fairness, efficiency, and interpretability. And now we elicit the preferences of users over these policies. And this is a very complicated problem because we looked at 20 features for each of the policies. Here we'd like to minimize worst case regret. I'm showing the results for regret because it's often how policymakers think. Our approach is shown in red, and the other colors show different approaches from the literature. Blue is the random approach, where I just select queries at random. What we can see is that as we ask questions on the x-axis here, I have a number of questions when there's no inconsistency in the responses and when there is inconsistency in the responses. And we can see that our approach has far lower worst case regret than existing methods. So in other words, the regret that we can guarantee with the questions we ask is a lot lower with our proposed approach than with all other methods from the literature. Not only this, but one may think that, well, worst case regret is a little bit pessimistic. Let's look at the worst case true regret. This is the actual regret exhibited by the agent, so not our worst case estimation of it, and we're taking worst case over agents. What we can see is that if there's no inconsistency after just 7 queries, we can make recommendations that are basically the best possible, that have regret 0, and really low regret if we have inconsistencies. This translates also to making recommendations that are ranked higher. For example, our approach without inconsistencies can recommend the top item, of course, after 7 queries, and an item that's ranked around 5, no matter how many queries we ask, compared to other approaches, which offer items that are ranked 10 or worse. A natural question you may ask is, what happens if our model of uncertainty is misspecified? So I say that I'm going to have a certain amount of inconsistency, and actually it's a lot different, the amount of inconsistencies in the responses that I get. And what we show is that actually, because our model is robust, it actually turns out to be robust to this ambiguity in the model. And we see that, for example, possibly the worst number on this figure is for offline elicitation, where we see that if we've modeled inconsistencies wrong, we recommend an item that's actually ranked 3 lower than originally, or 2.5 lower on average. So, so not too bad. We are deploying this currently first on Amazon Mechanical Turk, where we're collecting data as we speak. And then later on, we'll deploy it also on policymakers to get their preferences. Meanwhile, we're working closely with LAHSA to actually discuss a menu of fairness definitions for data-driven resource allocation that we've recently developed. So this is a paper in preparation for submission to FACT, where we've defined a whole host of metrics for measuring fairness of a resource allocation system at various steps. So in the allocation step, in the outcome step, and whatnot, and this under observational data. We are also discussing 2 approaches for optimal and fair allocation with them. One is based on the optimal prescriptive trees framework that I discussed earlier, where we're able to design policies that satisfy the budget constraints in the long run, that are fair and that are interpretable from this observational data. And we also have an approach that actually devises provably optimal policies among all policy classes that exist, that are based on this bid price approach from revenue management that we have generalized to the setting where both resources and individuals arrive online and where we don't know the outcomes of a match. And we're basically eliciting their preferences over these fairness definitions and over these policies that have arguably very different interpretability characteristics. As part of this work, we've devised a suite of tools for learning optimal decision trees and optimal prescriptive trees, involving also fairness constraints, and that work also when there are distribution shifts between training and testing. I'm happy to discuss this after the talk. At this point, I'd like to pause and ask if there are questions before I move on to the second part of my talk. All right, so the second part of my talk is concerned with biodiversity conservation, and this is work led by my PhD student, Ying Xiao Ye, and undergraduate student, Chris Doring. What got us looking into this problem is the fact that nature is declining at rates that we have not seen before. The rate of species extinction is accelerating. You're probably hearing about this all the time in the news, and this is having great impacts on people around the world. What's really dramatic about this is that we are the cause of these extinctions. In particular, most species extinctions are due to human-induced degradation. So what this means is that we build roads, we build cities, which basically destroy the habitats on which these animals rely. For this work, we're partnering with Panthera, and in particular with Hugh Robinson, who's Panthera's Director of Applied Science. Panthera is an NGO dedicated to preserving wildcats. With Hugh, we agreed that it would make a lot of sense to focus on protecting the jaguar in South and Central America. Why the jaguar? Because the jaguar is what is called an umbrella species, meaning that if you protect the jaguar, you'll actually end up protecting all the animals that belong in its ecosystem. So it's somewhat sufficient to protect the jaguar. So how does conservation actually work? When you're an organization that's making such conservation decisions, you're usually given a budget over time. What this means is that you get some funds in year 1, some additional funds in year 2, and so on and so forth. However, so you can use these funds to protect some parcels of land. But the thing is that anything that you don't protect risks becoming developed, meaning it could be that humans go and destroy all the trees, they build farms and whatnot, and these parcels of land will be lost forever. Also, there's significant uncertainty in projected human land use, meaning I don't know if I don't protect a parcel, which parcel will become developed first. At the same time, we have what we call endogenous uncertainty. What this means is that what we protect can actually not become developed. So we can control the set of possible realizations of the uncertain parameters. At the same time, we'd like the protection decisions that we make to be robust to uncertainty, meaning that no matter what humans do, we'd like to make sure that we save a maximum number of animals. Otherwise, ecosystems risk becoming lost forever. At the same time, we'd like these protection plans to be data-driven, so to use the best data that we have at our disposal, and adaptive, meaning that no matter that we have an action plan, no matter what humans decide to do. So a natural question you may be wondering is how are decisions about conservation currently made? Well, interestingly, they're being made using optimization as part of a conservation planning software called Markson. Roughly speaking, what this software does is it solves an optimization problem of this type, where for each parcel I, it decides whether to protect it or not. It's trying to minimize the conservation cost while ensuring that at least TJ animals of type J are saved, where Rij is the number of animals of species J in parcel I. The issue with this model is that it does not account for the probability of development nor of the endogenous nature of the uncertain parameters in this problem. And arguably this matters a lot. Why? Because it's probably not worthwhile for me to spend a lot of funds saving a parcel that's going to have lots of jaguars in it if there's very low probability that this parcel will get developed. So we propose a formulation that's going to account for uncertainty explicitly. So here I'm going to get a little bit technical for a bit, but I think you're going to get the intuition. So here XIT are going to be my decisions, and XIT will be 1 if and only if I decide to protect parcel I on or before time t. And XIIT will be the decisions made by humans, where basically we're saying that XIIT will be 1 if and only if parcel I has been developed before time t. And this gives us the following formulation. I know it looks scary, but I'm going to parse it and it should become very intuitive. So our decisions in this problem are the X variables, so which parcels we protect, XIT being 1, as I said before, if we protect parcel I on or before time t. All our decisions are adaptive, so they are allowed to change depending on the realization of the uncertain parameters, so of the development decisions made by humans. And we have various constraints. The first constraint is a budget constraint. It says that the cost of conservation at time t across all parcels cannot exceed my budget for time t. This constraint says that if a parcel has been developed before time t, I cannot protect it between time t minus 1 and time t. This constraint says us that if I've protected the parcel at time t minus 1, it must remain protected at time t. And I'd like this constraint to hold for all possible realizations of the uncertain parameters, and I'll get back to the definition of this guy in a moment. We want to select these actions X in a way that's going to minimize the worst case loss, meaning the worst case number of jaguars that are in parcels that become developed. So I look at the end of the planning horizon, what parcels have become developed, and I try to make their loss as small as possible. So the number of jaguars that were present in those parcels as small as possible. We want to hedge against all possible realizations of the uncertain parameters of the development actions in this uncertainty set U, which depends on the policy that we use to protect parcels. In particular, if I've protected a parcel on or before time t-1, it can no longer become developed in the future. So it's an uncertainty set that's going to depend on the choice of decisions that I make. This problem is quite hard because it involves this policy-dependent uncertainty set. It's actually really scary, and I don't think there exists a method for solving it off the shelf. And it involves also constraint uncertainty, making it even harder. What we show is that it's possible to obtain an equivalent reformulation that does not involve any uncertainty in the constraints, and where the uncertainty set does not depend on the decisions, provided we adjust our objective function in a way that it only accounts for losses that happened before we had a chance to protect a parcel. So it changes the way of accounting. This problem, although still hard, is somewhat amenable to existing solution methods, since the uncertainty set is now exogenous, so independent of our decisions, and since we have only objective uncertainty. Let me now show you our results on data shared with us by our collaborator, Dr. Hugh Robinson, and data found online by our undergraduate student. So first of all, we have the jaguar density. So this will tell us which parcels have the most jaguars. This graph tells us the protection cost. So this is the cost that was calculated based on a model of Bomford and al. That uses various elements such as mean temperature, mean precipitation, canopy, etc. to predict the cost of protecting a parcel. We also found development threat data from the LAHSA SEDAC, which is the Socioeconomic Data and Application Center, that basically also motivates our approach. If you look here, we have several parcels that have a very large number of jaguars, but actually that have very low chance of becoming developed. And this is precisely what our algorithm will leverage to make strategic decisions. We use this data that we have at our disposal to build uncertainty sets. In particular, we're going to cluster parcels based on their threat level and their characteristics. This is going to define a neighborhood for each parcel, which is kind of the parcels that are near it, that are similar to it. And we're going to then simulate development using a model that's very popular in ecology called the cellular automata model, which basically allows developments to spread from one parcel to the other, or new developments to start on their own. From this simulation, we obtain for each parcel the probability that it will get developed, which allows us to build an uncertainty set that involves all the realizations that have a likelihood greater than lambda of materializing. So the lambda here is really going to help us tune how robust we would like our model to be, with lower values of lambda corresponding to models that are more robust. Let me show you some preliminary results before wrapping up. So on the figure on the left here, we're showing the number of jaguars that are in protected parcels. And here we can see that the marksan somewhat dominates. So the proposed approach from the literature dominates in terms of jaguars in the protected parcels. But I'd like to argue that this is not what we care about. What we care about is about not losing jaguars, meaning we care about the number of jaguars that were actually in parcels that became developed. And if we look at that metric, actually now we see that marksan loses a lot more jaguars than our approach, no matter what the budget that we have at our disposal is. We have a very similar figure looking at connectivity, meaning, when we are doing conservation actions, we'd like the parcels that do not get developed to be as connected as possible, so that jaguars and other species have the opportunity to travel throughout these connected parcels. And we similarly have a greater number a better connectivity in our approach when we look at the parcels that have not been developed than Marxon. So I'd like to conclude now by saying that, I hope to have illustrated that through this. I hope to have illustrated through these two examples that new research in data-driven optimization is needed to address important societal problems. I hope to have convinced you that there's great benefit in collaborating with community partners, both because they can help us identify and understand important problems of our time, but also because it can help us actually deploy our algorithms to be able to make a direct impact on society. There's many more interesting use-inspired research questions that we're looking to address in our lab that relate to uncertainty in data, to distribution shifts, to missing data, and to the observational nature of the data that we're working with, that I look forward to addressing. I'd like to acknowledge support from various organizations, including the Homelessness Policy Research Institute, the Conrad Hilton Foundation, the Home for Good Foundation, the National Science Foundation, and USC. These are the papers I used in my presentation. Mostly I presented this paper. However, these two papers, sorry, the first one and the last one. However, I also mentioned 3 papers that I used in this research. These are some related works in preference elicitation. Before closing, I'd like to tell you about a conference we're organizing in LA at the interface of artificial intelligence, machine learning, operation research, and constraint programming. The deadline is upcoming and I encourage you to submit. There will be a masterclass on bridging the gap between ML and optimization that should be of great interest. Thank you very much for your time, and I'll stop here. And I'll be happy to take any questions you have.
Thank you, Phoebe, for the nice talk.
Thanks.
So we realize that we are just a bit over time because we started late. But if you have any questions, feel free to post it in the chat box or in the Q&A box. Yep, so it looks like somebody is waiting on the fence, so I will jump in to ask a question for myself. So for the first part of the talk, so you kind of described this 2 phase decision making. The first by designing which question to ask, and the second by optimize over the worst case utility. So my question is that it would be possible to replace the second part using some other measure or characteristics about the uncertainty set, right? So for example, from the knowledge learning perspective, can we ask a question to how can I select the best subset of question to minimize the size of the utility sets, or to kind of shrink the width of this uncertainty set in certain direction, or so on. So is it possible to adapt the existing approach to this other characteristics?
Yeah, sure. It should be possible. I'm trying to think how it relates to the existing literature. So you could certainly, modify this inner problem to have a different objective than the one that we have. I'm trying to think, would you gain anything relative to what is done in the current literature? So in the current literature, for example, one approach is to say, I'm going to select the queries in a way that they're going to pass as close as possible to the analytic center of the uncertainty sets. And then some approaches also look at the direction of the cut introduced, basically to try to result in 2 sets that are as small as possible. I feel that the existing methods are to some extent optimal in tackling this problem. I don't know that they have a proof of optimality in terms of shrinking the uncertainty set as much as possible, but they have a very nice intuition in terms of that's what they do. I think here we were mostly motivated by saying, well, we're not interested in reducing uncertainty so much as we're interested in reducing uncertainty in the directions that matter for the recommendation. However, yeah, I agree that one could explore different objective functions. I don't think that the main difference, I guess, if we do this, is that existing methods from the literature don't work when you're asking multiple queries at once. They work to only identify one query at a time. Yeah, so in that sense, if we're able to change our objective function to something that you're mentioning, then you would have a method that works for this offline setting that we studied and that shrinks uncertainty as much as possible, as opposed to making good recommendations.
I see. Yeah, thank you.
Yeah, thanks for the question, Ruwei. Any more questions? They can be softer questions if you feel intimidated. Do we have master students here, Ruwei, or we have PhD students? What's our audience?
So I see a question from the Q&A. The question is, in the second topic, the number of jaguars at each location will change depending on where to develop. How did you predict decision-dependent numbers? Any prediction uncertainties are considered?
That's a great question, and Shane, thank you for it. So this is a hard question. So I don't know if the number of jaguars at each location will necessarily change depending on where you developed. One could argue that if you develop, you don't lose all the jaguars in that location, which is what we're assuming right now. I believe that our model could be adapted to the setting you discussed, you propose. I don't know that it will yield massively different situations here, massively different results. Did that answer your question, Unjin? Okay, thank you. All right.
So another question. So these max or min problems in the first part of presentation about utility functions, you are considering convex sets so that they have solutions, correct?
So which sets are convex? The only sets that are convex are the uncertainty sets. If you assume that the recommendation set is convex, then the problem in the max-min utility setting becomes actually really easy to solve. And the other sets, which are the query sets and the response sets, are non-convex. In regards to the uncertainty set, you're absolutely right that they are convex, and even when we model inconsistencies, they will be convex sets. The main motivation here is that these sets capture all the information we have about the utilities, and that they can be easily updated, probably more easily than if you model using distributions, where you'd have a lot of sensitivity to the prior distribution you assume, and where the updating would have to rely on Bayesian updating rules, which are fairly challenging to do in this optimization setting. So we're only taking here guaranteed information that we have about the utilities. So the motivation is to have a model that's low on assumptions, and it so happens that you're right that it also gives a convex set. Does that answer your question, Juan? Okay, thank you. All right, Ruwei, what do you think? We wrap it up?
Yeah. So if no more question for now, let's end the session. And I would like to thank Phoebe again for visiting us virtually. So she has a full day schedule. So we are very grateful for her time and also for the great seminar she just gave. And so I would like to also thank the audience for their attention. So this concludes the MIDAS seminar today. Thank you.
Thank you all so much, and thank you, Ruwei, for the questions. Thank you, everyone, for taking part. I really appreciate you joining.